Is it visible?
Yes, sir. Yes.
Okay. So last day we were discussing about the representation, time domain representation of a DT-LTI system, discrete time LTI system. So we started from the premise that from a knowledge of the continuous time LTI system, what did you find? That the most general mathematical model in the time domain for the continuous time LTI system is one that relates the output and the input through a constant coefficient differential equation. So if you want to perform the same task as done by this continuous time LTI system by using a DT-LTI system, you must sample the signal xt first, and then there will be the DT-LTI system which will serve the same purpose as the continuous time LTI system, say a particular filtering operation. Therefore, the DT-LTI system, its representation, the representation of yn with xn will be governed by the equation that I have written here. I think that it's clear. Now, each derivative on the left-hand side can be represented by a constant coefficient difference equation. Similarly, in this case also, each derivative of x, it can be represented by a constant coefficient difference equation. Because in both these cases, I am generalizing by considering the ith derivative. Therefore, in place of this expression, what you can write will be something of this form, an equation of this form. All right, is it clear? Each such derivative, it can be represented by a constant coefficient difference equation. So ultimately you will end up with that type of an equation. The left-hand side will be this one, the right-hand side will be that one. If you ask me to explain it more clearly, just see here that this was the expression relating the sequence Zn and Sn in our observations that we made. All right. So now if you want to use that knowledge here, I must put it into that expression. All right, this one. Oh, so people are coming in. So what should I write here? In place of dy dt, diyt dti, what should I write here? I should write here the ith expression for the ith derivative evaluated at t equal to n tau, isn't it? So what will that be equal to? Just see here. Oh my goodness, people are still coming in. Just 1 minute. These summation here, there will be a summation I equal to 0 to capital N. All right, then AI will be there. AI. After that, what will be appear? What will appear here? A0i, isn't it? AI, here you should have A0i. Then what will be the term? Sn minus I. Just tell me. It will be yn minus I, isn't it? Plus A1i. In this way, can you see it?
Sir, I'm not able to get the things.
Okay,
Please
okay.
repeat.
Each derivative here, just go back to the earlier case. In our earlier discussion, we have seen that if the output of the system Zn tau is the ith derivative of the input, then what will happen? Zn will be A0i Sn plus A1i Sn minus 1 plus A2i Sn minus 2, etc. up to Aii Sn minus I. So here what can you write? Just a replica of this one. You can write here, in place of this derivative evaluated at t equal to n tau, you can write A0i yn plus A1i yn minus 1 plus A2i yn minus 2 in this way. All right, ith order difference equation. Similarly here, in place of this derivative, what can you write? A0i xn plus A1i xn minus 1 plus A2i xn minus 2 plus A3i xn minus 3 in this way up to which term? Aii Sn minus I. So here the last term will be Aii xn minus I. Here the last term will be Aii yn minus I. So that ith order difference equation will be multiplied by Ai. Here the ith order difference relation should be multiplied by Bi. Therefore, if I combine this thing, you will get an expression of this form. Now is it clear?
Yes, sir.
Okay. So that is called a constant coefficient difference equation relating the output yn and the input xn. All right. If consider the case when capital N is not equal to 0. In that case, you can just split up this summation into two parts. Alpha 0 yn, if you take that term alpha 0 yn out of this summation, what will remain will be summation over I equal to 1 to n, then alpha I yn minus I. So alpha 0 yn will be there plus summation over I equal to 1 to n alpha I yn minus I. This summation can be transferred to the right hand side. That's what I have done here. So A0 alpha 0 yn is given by this expression, or yn will be given by the expression shown here just by cross multiplying with alpha 0. Have you got it? So if you have not written it last day, you may please write it down. That is the case for n not equal to 0. We will later consider the case for n equal to 0. But before that, we have some more things to discuss. So regarding the generalized expression equation for representing the DT-LTI system, that much is all right.
Sir, last day we are doing with a backward difference relation, no?
Last day we stopped here. Last day we stopped here. This was the expression where we stopped last day. Backward difference relation, etc. that have already been completed. So here we were considering backward difference relation, and thereby we were getting these expressions for the second order derivative, third order derivative, ith order derivative. Then we were utilizing those expressions in representing a general discrete time LTI system by a constant coefficient difference equation. All right. So we were getting this expression. That is the expression. I've written it. If you haven't written it, please write it down.
Done.
So it directly expresses the output at instant n in terms of previous values of input and output. Now in this expression, equation 2, if you take the Z transform of both sides, use the time shift property of Z transform. So what will you have on the left hand side? Alpha I, because there is the term yn minus I, alpha I times z to the power minus I yz. Here you will have beta I times z to the power minus I times xz. So the ratio yz by xz, which we call the z transfer function, it will be obtained in this way. So that is the generalized expression when n is not equal to 0 of the transfer function of the DT-LTI system. Now later on we'll consider special cases. Here in this expression, just see that how have I moved from that ratio to this one. I have kept the numerator intact, and in the denominator what have I done? I have taken out the term corresponding to alpha 0. All right, that term corresponding to alpha 0. I have divided the numerator by that alpha 0. So here you have 1 plus summation over I equal to 1 to n alpha I by alpha 0 z to the power minus I. That could also have been obtained simply by taking the Z transform of this equation, both sides of this equation. Next, we will discuss the properties of discrete time convolution, that is convolution sum, and interconnection of LTI systems. In your signals and systems course, you have studied at length the properties of convolution integral, the properties of continuous time convolution and interconnection of continuous time LTI system. So these discussions will just be a mapping of those properties. Just a mapping between those properties, just it will be changed to a certain extent to fit it to discrete time convolution.
Sir, can you please explain it again? How that ZZ last expression has come in the...
This one?
Yeah. Yes.
So if you take out alpha 0 term, if you take out alpha 0 term out of this summation, what will you have? Alpha 0 plus summation over I equal to 1 to n, alpha 0 plus summation over I equal to 1 to n, alpha I z to the power minus I. Is that all right? If I take out alpha 0. Now if you divide the numerator and denominator by alpha 0, what will happen? In the numerator you will get alpha 0 here. In the denominator you had the term alpha 0. So that the division of alpha 0 by alpha 0 will result in 1 plus summation over I equal to 1 to n alpha I by alpha 0 z to the power minus I. All right, or should I explain once more?
No, sir, it's clear.
It's clear. Properties of discrete time convolution and interconnection of linear time invariant systems. Say we have a DT-LTI system, and when this system is excited by a unit sample sequence or unit impulse sequence, delta n, the output is Gn. Then Gn is called the impulse response sequence of the DT-LTI system, or waiting sequence of the DT-LTI system. Waiting spelling is W-E-I-G-H-T-I-N-G, waiting. Why it is called waiting sequence, you'll understand. Now let's consider that this DT-LTI system is excited by any sequence xn whose z transform is xz. So Gn is the impulse response of the DT-LTI system. Therefore, it's a property of the system. Therefore, this DT-LTI system represented by the block, I can just put in Gn here because this is a property of the system. Its z transform is Gz. All right. Now, the output is represented by Yn, its z transform is Yz. You know that Yn will be the convolution of Xn with Gn. Now, therefore, Yz will be Gz into Xz. So, here, just see that output Yn of a DT-LTI system, when you excite the system by an input Xn, it can be expressed as a convolution of Xn and Gn, where Gn is the impulse response of the system. Now, to put it right from the basics, say we are exciting the DT-LTI system by the sequence Xn. X0 is the sample value at n equal to 0. At n equal to 1, it's x1. At n equal to 2, it's x2. In this way, it's progressing. At n equal to minus 1, it's x minus 1. N equal to minus 2, it's x minus 2. So, do you understand that this sequence xn, it can also be represented in the way that I have written here in terms of impulse sequences? Say this is the sequence xn. Then this sample x0, if other samples are absent, only this sample is present, x0. Can't you represent it by x0 delta n? Because delta n is simply such a vertical line with magnitude 1. So x0 delta n will definitely represent that vertical line with height x0, isn't it? Now this one, at n equal to 1, the sample value is x1. So just if you want to express it as a sequence, can't you express it as x1 delta n minus 1? Because forget about the other samples. If you have delta n minus 1, it means you have a vertical line here whose height is unity. So if the height is x1, this sample can also be expressed by this expression x1 delta n minus 1. In this way, so the entire sequence, it can be expressed as x0 delta n, x1 delta n minus 1 plus x2 delta n minus 2, etc. And on this side, x minus 1 delta n plus 1, x minus 2 delta n plus 2, etc. That means xn can be represented by this summation, means if you put it in the compact form, summation over m equal to minus infinity to plus infinity xm delta n minus m. I have just put this summation in a compact form. This expression is nothing but the expression for a convolution sum expression. So it's actually xn into xn convolution delta n. So this is from the basics. Instead of straightway writing that yn will be from xn convolution gn, I am trying to proceed from the basics. Although we know that ultimately yn will be the convolution of xn with gn. Now, if that is the case, if you agree with this expression, then corresponding to, you must understand this DTLTI system, the same DTLTI system that we were considering earlier, whose transfer function is gz. If you excite it by delta n, output is gn. If you excite it by delta n minus m, output will be gn minus m. It follows from the property of time invariance. If you excite the system by xm delta n minus m for a given input sequence, once you have selected the input sequence, the sample values of the input sequence at different sampling instants, that gets fixed once and for all. So xm delta n minus m means a constant times delta n minus m. Corresponding to that, what will be the output? Xm into gn minus m. It follows from the property of proportionality because it's a linear system. Then if you have a sequence xk delta n minus k plus xm delta n minus m as the input, the output will be from the property of superposition that this linear system should obey, xk gn minus k plus xm gn minus m. Now if you generalize, yn will actually be equal to the sum of all these terms, xm gn minus m with m extending from minus infinity to plus infinity. That means yn will be a convolution of xn with gn. Also, yn will be a convolution of gn with xn. That means it can also be represented in this manner. So here in this summation, just see, it is a weighted sum of the different samples of xn, isn't it? This is simply a weighted sum of different samples of the input sequence. And what are the weights that have been assigned to different input samples? Gm. The weights are the samples of the impulse response. The samples of the impulse response, they serve as the weights. All right. So that's why another name for the impulse response sequence is the weighting sequence of the system. If it is clear, you may write down. Otherwise, if it is not clear, if there is anything still not clear, you may point it out. I try to explain it once more. You've done it.
Yes, sir.
Yes, sir.
I have written here output yn of a DTLTI system excited by input xn can be expressed as a convolution of xn and gn. That the output yn can be represented by a convolution, I have tried to prove it from the basic expression, from the fundamentals. এই আমাকে একটু চা দিও না, শুনছো? চা দিও না। Done it?
Yes, sir.
Have you understood why it is called weighting sequence? In absence of GM, if GM, I mean, here, if you have summation over M equal to minus infinity to plus infinity, xn minus m, what would that represent? Simply a summation of the different samples of the input sequence. But now, instead of having the sum, each such input sample value is multiplied with GM. So it means that this is a weighted sum. And the weights are the samples of the impulse response. GM means it represents the sample of the impulse response. So these samples of the impulse response, GM, for different values of M, they serve as weights for these input samples. They are multiplied by the weights and then the summation is taken. Now come to the properties. First is the commutative property. Convolution of xn with gn is same as convolution of gn with xn. From system point of view, the implication is that if you have a DTLTI system with impulse response gn and you excite it by xn, under such condition, if the output is yn, then if you have another DTLTI system whose impulse response sequence is xn, now if you excite this second system by the sequence gn, then you will get the same output yn as obtained for the first system. Move on to the associative property. The associative property is written there. The statement of the property: convolution of xn with a certain sequence g1n, and then if this result is convolved with another sequence g2n, it is same as the right hand side. What do you have on the right hand side? Convolution of xn with the result of convolution of g1n and g2n. So what's the implication of this property from system point of view? You have come across such properties in case of continuous time system. So what's the significance from system point of view? From system point of view, how can you visualize the left-hand side of the equation 5? As if there is a DT-LTI system whose impulse response is G1n, and the result of convolution bracketed here, what is that? It is the expression for the response of that system when it is excited by xn. So that is the implication. That is what is represented by this bracketed term. Output of a system with impulse response G1n when excited by xn. That result is convolved with G2n, means the output of the system G1n, it's fed to a second system with impulse response G2n. So convolution of that with G2n means the left-hand side, if it is represented by yn, it is the ultimate output of the second system. All right. So as if two systems are there, they are in cascade. Two non-interacting DT-LTI systems are in cascade. And the output of the cascade combination is given by the left-hand side, which we will represent as yn. It must be equal to convolution of xn with the result of convolution of g1n with g2n. It means that this is the case. And what is the right-hand side representing? As if you have a system with impulse response gn equal to g1n convolution g2n. Input here is xn and output here is also yn. So this system and that system, they are identical. Therefore, it implies that if you have two DT-LTI systems in cascade, then the overall impulse response, the impulse response of the cascade combination will be the convolution of the individual impulse responses. Just see here. In the Z domain, what will happen if this has a transfer function G1Z, that one has a transfer function G2Z, the equivalent system will have a transfer function Gz equal to G1Z times G2Z. So convolution in time domain manifests as product in the Z domain. You know that. Whatever I have said, I have narrated here. I have just, this text, it represents whatever I have said. I have considered two LTI systems in cascade. In this way, if you have capital L number of DT-LTI systems in cascade, having impulse responses G1n, G2n, G3n up to GLN, then this cascade combination, the complete cascade combination will have an impulse response Gn, which is the result of convolution of G1n with G2n, then with G3n, then with G4n, etc. up to GLN. In the Z domain, the transfer function will be the product of capital G1Z, capital G2Z, etc. This is GLN. So here you have Gn equal to G1n convolution G2n in this way up to GLN. Next property is that of, this is called distributive property. Statement is given in equation 6. If you have a look at the right hand side of equation 6, you will find that first term on the right hand side, if I represent it by y1n, then what is y1n? As if you have a DT-LTI system with impulse response G1n, you are exciting it by xn, and the output is y1n. The first term on the right hand side. Second term on the right hand side is that as if you are having a system, another system with impulse response G2n, it's excited by xn, and the output is y2n. Result of this convolution, if I represent it by y2n, that is the implication. So right hand side is actually the sum of y1n and y2n. So same sequence xn is exciting two different DT-LTI systems. And ultimately, the output of the two DT-LTI systems are added to generate the right hand side. So what type of a combination is this one? Two DT-LTI systems in parallel. If such is the case, then if you represent the right hand side by yn, it should be equal to the left hand side. What do you have in the left hand side? You have a certain sequence gn, which is the sum of g1n with g2n. And left hand side, which is equal to right hand side equal to yn, is simply the convolution of xn with gn. That signifies that if you have two DT-LTI systems in parallel, then the parallel combination will have an impulse response which is the sum of the individual impulse responses of the subsystems. That is the implication. All right. The output of this system G1n, you may write here that it's y1n and this is y2n. So this parallel combination has an impulse response Gn, which is sum of G1n with G2n. Gn is G1n into G1n plus G2n. What will be the transfer function of the parallel combination? Z transform of G1n is, say, capital G1Z. Z transform of G2n is capital G2Z. So those are the transfer functions of the two subsystems. In the Z domain also, the overall system transfer function Gz, which is the Z transform of Gn, that will be the sum of the individual transfer functions. So Gz will be G1Z plus G2Z. Unlike the cascade combination. Here, both in the Z domain and time domain, there will be summation. So here is also a generalization that if you have capital L number of LTI systems, DT-LTI systems in parallel with impulse response G1n, G2n, etc., and the common input is xn, then the combination of the overall L number of systems in parallel, that will be the sum of the individual impulse responses. Have you written it?
Yes. Yes, sir.
Yes, sir.
This is the pictorial depiction of what I have stated. In the subsequent properties that we will point out, there will be something that will help you in actually obtaining the convolution of two sequences, performing the convolution of two sequences. This is G1n, G2n, G3n, in this way GLN. So the combination has an impulse response, which is the sum of the individual impulse responses. Just give dotted lines here. Instead of firm lines, use dotted lines here. Similarly here also, dotted lines. There.
Done, sir.
Now have a look at the time shift property.
Sir, can you go up, please? I
Oh
haven't
yes,
completed.
yes, sure. Need not hurry. Be comfortable and draw. Now look at the time shift property. If yn represents the convolution of xn with gn, then I am proceeding leftward from the right hand side. Yn minus k will be the convolution of xn minus k with gn, or gn minus k with xn, or xn minus k1 with gn minus k2, or gn minus k2 with xn minus k1, where k1 plus k2 is equal to k. You understand? So that is the implication of the time shift property. It's not that ynk will be the convolution of xn minus k with gn minus k. Don't think that. But this will be the case. But k1 plus k2 will be equal to k. Convolution with impulse, it's known to you. Xn convolution delta n will be Sn itself. Do you remember, in case of continuous time signals, what will happen if xt is convolved with unit step? Can you point out the result without actually performing the convolution? What will really happen?
So it will be integration of minus
Right,
infinity to
right. If when a signal xt is convolved with ut, it tantamounts to integrating xt. Similar properties are here. Convolution with impulse, it's known to you. Convolution with step. Convolution of xn with un, same as un convolution xn, will be given by that expression. All right. So it is the equivalent of integration. The summation is the equivalent of integration in the continuous time case. It is called accumulation. The convolution with step results in accumulation of the signal xn. Have you written it?
Yes, sir.
This property you must remember carefully. This is called width property. You had identical property in case of continuous time convolution. Suppose you have the sequence xn, it extends from minus n1 to plus n2, and a sequence gn extends from minus m1 to plus m2. These are integers, of course. Then yn is the convolution of xn with gn. I have already stated. Then yn, which is the convolution of xn with gn, it will extend from minus n1 plus m1 to plus n2 plus m2. All right. That is very important in case of determination of convolution by performing time domain computation. Now, I have stated that xn extends from minus n1 to plus n2. it implies that the sequence xn has a width of wx equal to n1 plus n2 plus 1 number of samples. Gn extends from minus capital M1 to plus M2. Gn has a width of capital M1 plus capital M2 plus 1 number of samples. Yn, it will have a width of Wy, which will be the sum of the widths of xn and gn minus 1. Sum of wx, wg, then you have to subtract 1. All right. So that will be the width of yn, which is the convolution of xn with gn. So this property you must remember carefully. Other properties you will remember automatically, but this one is important. Consider this problem. You have been asked to find out the convolution of two sequences. Xn represented in this form. Obviously, the vertical arrowhead represents the sample x0. Similarly, here the vertical arrowhead represents the sample g0. How do you perform the convolution? There are several ways to tackle this problem. You can use straightforward convolution, or a better one is what I'm trying to show here. You'll also find it in the textbooks. First, just note that edge of xn, this is x0, this is x minus 1, this is x minus 2, this is x minus 3. So the left edge or left end of xn is minus 3, isn't it? The right edge or right end of xn is 0, 1, 2. So right edge is n equal to 2, left edge is n equal to minus 3. Here, in case of gn, what is the left edge? It is n equal to minus 3, and right edge is n equal to 3. So if you convolve these two sequences, then what will be the left edge of the sequence? And what will be the right edge of the sequence? Left edge will be n equal to minus 6, minus 3, minus 3, minus 6. And right edge of the convolution will be plus 3, plus 2. That means plus 5. All right. So width will be 12 samples, I think. Now, how to perform this convolution? Remember that the problem could well have been given in this form, that xn is the excitation to a certain DT-LTI system whose impulse response Gn is given as follows. And you are asked to carry out time domain operation to obtain the output sequence. All right. It could have been given in that manner also. It could have also been given in a form that say this Xn is the impulse response of a certain DT-LTI system, Gn is the impulse response of another DT-LTI system. Those two DT-LTI systems are connected in cascade. Then what will be the impulse response of the cascade combination? The same problem could have been stated in different languages. Now come to the solution. I'm just taking it on. Next page. Have you written down the problem?
Yes, sir.
Yes, sir.
Just see that here I have formed a table. I've just formed a table. So the first row are the samples of Xn. And this left-hand side column, these are the samples of Gn. Just check whether what I have done is correct or not. If that is correct, then for every pair of samples from Xn and Gn, we obtain the product. That means we fill up these boxes by the products of different samples of Xn and different samples of Gn. For every combination of a sample from Xn and a sample from Gn. So 1 into 2, this is 2, 3 into 2 is 6, minus 4 into 2 is minus 8, etc. 1 into 8 is 8, 3 into 8 is 24, minus 4 into 8 is minus 32, etc. In this way, I have filled up all the boxes. Now, your duty will be just to draw some demarcating lines, some lines in this direction. Because I couldn't draw it in that manner, I have used different colors. So just see the first sample of convolution, the leftmost sample of convolution will be 2. So this is 2. Next sample of convolution will be, you draw a straight line in this manner. So you will add up what I have represented in red. That means 8 plus 6, 14. Next sample of convolution will be, you just draw a demarcating line here. So you add up, according to my table, you add up these blue numbers. 6 plus 24, 30 minus 8, 22. All right. Next, you draw a line here. So you add up this violet colored lines. Minus 5 plus 18, that means 13 minus 32 minus 4. That will result in minus 23. Just check. Right? Then you add up these blue numbers. That is minus 41. Next, you add up these red numbers. 71 probably. Then you add up these black numbers. 82. Green numbers minus 61. Blue numbers minus 37. Red numbers 52. Then these two numbers, violet colored numbers, 17, and lastly this one, minus 3. So you have obtained the values. Remember that I have already pointed out that the left edge of yn will be minus 6. All right. So this is n equal to 0, n equal to if this is n equal to -6, this is n equal to -5, this is -4, -3, -2, -1, and this is n equal to 0. Then those will be the terms for n equal to 1, n equal to 2, n equal to 3, n equal to 4, n equal to 5. I have already pointed out that the right edge or right end of yn, it should be 5. The sum of the right ends of xn and gn. All right. So this is done, I think. After you have completed writing, please let me know. There is another problem. After completing that problem, I'll conclude today.
Done.
Yes, sir. Done.
Done?
Yes.
Yes, sir, done.
So here, the next problem, we have been asked to find the closed form expression for the convolution of the sequences xn and hn. 0.5 to the power n un minus 2 and hn equal to 0.7 to the power n un minus 1. The expressions have been given, and you are also asked to find out the expression for the result of convolution of xn with hn. Not merely the sample values. They've written it. So yn, I am representing the result of convolution of xn with hn. It's same as the convolution of hn with xn by yn. So I have started from the basic expression for the convolution sum here. I have substituted the expressions for xk and hn minus k. Just see. So then I have maneuvered. k greater than 2, uk minus 2. For k less than 2, for k less than 2, it will be 0, uk minus 2. That's why this is the expression. All right. Then simply a maneuvering is there. 0.7 to the power n has been taken out. So whatever remains within the summation is, the power is k and minus k here. So you know it's a progression. So you can find out that summation. Ultimately comes out as 1.75 times within brackets 0.7 to the power n minus 1 minus 0.5 to the power n minus 1. All right. Now the left edge of xn, from the expression you can easily find that the left edge of xn is n equal to 2 and the left edge of hn is n equal to 1. So left edge of yn will be n equal to 3. So actual expression will be that one times un minus 3. All right. To ensure that the left edge of yn is n equal to 3.
Done. Sir.
স্যার আপার লিমিটটা স্যার n কি করে ওটা স্যার একটা এক্সপ্লেন করলে।
Upper limit is n because both the sequences are causal sequences. All right. If you
Yes, sir.
observe the basic expression for the convolution, you will find that if both sequences are causal, all right, then the upper limit will be n.
Oh.
Go back to the original expression for convolution sum when I have discussed about that convolution property of Z transform. There you will understand.
Okay, sir.
Both of them are causal sequences. This one as well as that one. Okay, let me stop today here. You complete writing then. You decide the date for the next class, then let me know later.
Okay. Sir.
I have 2 classes tomorrow. Not tomorrow. Tomorrow I have 1 class and day after tomorrow I will be busy very much. So after that.
Okay, sir.
If you have any question, please feel free to ask any question. Done it.
Sir,
Ah,
sir, can you please go back to the earlier slide in discrete time differentiator?
yes.
Yes, so this one only.
Huh?
Slope of xt.
Slope of xt, right? Hmm.
Sir, I have not got the expression of y and t. How you have written the equation 3.
This
Okay,
one.
this one. Yes, sir.
Ynt is the derivative of xt at t equal to n tau. So what are the information available to the differentiator? Only sample values at the current instant and previous instant maybe, and the knowledge of tau.
Yeah.
These are the only things. So using this knowledge, the differentiator has to obtain the approximate slope of xt at t equal to n tau. It will never be able to obtain the actual slope. So here what I have done is that I have considered, I have joined the heads of two samples by a straight line, two consecutive samples, x n tau minus tau. I have exaggerated this portion, magnified. So this is x n tau, this is x n tau minus tau, this is x n tau. So what will be the slope? The actual slope can be approximated by the slope of this straight line, blue straight line. Do you agree with that? If tau is very small. So therefore, what is the slope of this straight line? The difference between the two, this height, all right, divided by tau. This width is tau. So x n tau minus x n tau minus tau. X n tau is this height, and it has a height of x n tau minus tau. The difference is the height of this right angle triangle. All right, and that divided by tau, tau, the base. That is the slope. You understand? So that's why I have written here y n tau, it's approximately x n tau minus x n tau minus tau by tau. That means 1 by tau into x n tau minus 1 by tau into x n tau minus tau. Is it clear?
Yes, yes. Yes, sir, now it's clear.
Okay. Any other problem?
Yes, sir, it is clear. No, sir.
Huh? You are saying no, sir.
No, sir.
Some problem.
No, sir, everything is all right.
Okay.
Yeah.
So can I wind up today?
Yeah, sure, sir.
Yes, sir. Thank you.
Okay, so please let me know next. You consult among yourselves and we know the date. Your result has come out for the the second year first semester result?
No, sir.
Not yet.
No.
All right. Thank you.
Thank you.
Thank you, sir.